Greetings, Chem 110H, Dr. Bevilacqua here. I'm going to go over the effect of a catalyst on equilibrium. So first off, catalysts are substances that speed up a chemical reaction. They could be small molecules, they can be surfaces, they often have precious metals in them, and they can be enzymes. And they typically work by binding and lowering the energy of the transition state. By doing so, they speed up a reaction, and they speed it up in both the forward and the reverse reaction. They speed it up by lowering the activation energy for the reaction. Because they speed up both the forward and reverse direction, they do not change the equilibrium constant, and we'll demonstrate that on the next slide. And catalysts found in biology and biochemistry are called enzymes. They're typically made up of proteins, but RNA can be an enzyme as well. And in fact, my PhD work was done studying enzymes made out of RNA. RNA enzymes are so-called ribozymes. They were discovered in the early 1980s, and their discovery led to the Nobel Prize in Chemistry. So I'd like to talk about an important specific example of catalysis, and on this slide we refer to the Born-Haber cycle, and this is an important reaction that takes nitrogen gas, as it's found in the atmosphere, very abundant, about 80% of the air is made of nitrogen, and it reacts with 3 equivalents of hydrogen to make 2 equivalents of ammonia. And the process of taking nitrogen out of the atmosphere and converting it into ammonia is referred to as nitrogen fixation. And plants have nodules in their roots, and they associate with symbiotic nitrogen-fixing bacteria in order to carry this process out. Ammonia, then, is very useful in biology. It can go into various metabolic pathways and can be used in a number of biosynthetic pathways as well. Ammonia is also extremely important in agriculture and is the basis for making a number of fertilizers. And this process can be catalyzed, in this case, by an iron silica catalyst. And if we look at the reaction, we can sort of understand why it needs to be catalyzed, because nitrogen is made out of a very stable atomic molecule, dinitrogen, which has this very stable triple bond. And because of that, this reaction is very slow, and in order to make it happen, it helps to have a catalyst. So here we provide a reaction energy diagram, a plot again of energy versus progress of the reaction. We have our 2 reactants on the left and our 2 equivalents of ammonia product on the right. And the transition state, as you know, is the highest point on this reaction trajectory. And the activation energy, E sub A, in the forward direction, or E sub A comma F, is the difference in energy between the transition state and the reactant state. We can also define an activation energy for the reverse direction, E sub A reverse, and that's the difference in energy between the same transition state and this time the products. Remember that this activation energy typically can be thought of as the breaking of bonds, and it's high in this direction because we need to break this very stable triple bond in nitrogen, as well as we need to break 3 single bonds in hydrogen. The effect of a catalyst, shown here in this pink color, is to lower the energy of the transition state. Remember, we said that enzymes and catalysts work by binding the transition state. This is sometimes referred to as the Pauling hypothesis on how enzymes work. And in doing that, we can talk about the effect of the catalyst mathematically as being delta sub cat. We're then going to put down a new equation, but one that should look familiar to you. This is called the Arrhenius equation, and it relates a rate constant, the ith rate constant, to its activation energy, E sub A sub I. And this looks very similar to the Clausius-Clapeyron equation that we talked about, scale height, as well as the Van 't Hoff equation that was presented in class for equilibria. And we can see a potential energy term, a bonding term for breaking bonds, and a kinetic energy term here in the numerator, in the denominator. So together this would be unitless and provide the value to which E is raised. We can then, once we calculate the rate constant, write down the rate law, and the forward rate is equal to the forward rate constant. Using the law of mass action, we just know it's times nitrogen, then times hydrogen, raised to a power, which is the coefficient in the reaction. And as the activation energy in the forward reaction goes down, what happens is that K goes up. It doesn't have as high of a mountain to climb anymore. And you can show that that's true mathematically. If you think about this particular mathematical equation, this is equivalent to A divided by E to the E sub A. And so if we make E sub A smaller, then we're reducing A by a smaller amount. We can also talk about what happens when the activation energy for the reverse reaction is lowered. Well, then that's going to increase the rate constant for the reverse reaction, just like what happened for the forward reaction. So the catalyst is speeding up the forward reaction, and it's speeding up the reverse reaction. What is it doing to the equilibrium constant? Well, you might guess that it's not changing it because it's increasing both the numerator and the denominator, and the effects might cancel out. And in fact, you would be right, but we can show this rigorously. And on this slide, I've gone ahead and written down the equilibrium constant. As we showed in class, it's the ratio of the rate constant for the forward and reverse reactions. And so we can then write that down. First, I have here the term for K sub F, and then I went ahead and put in the term for K sub R and divide those, and making a new constant from the division of two constants, as well as then applying appropriate math to the exponent, we can see that K is equal to A e to the minus difference in the activation energies, which turns out to be delta H divided by RT. What happens when we add the catalyst? Well, remember on the last slide that we showed that the activation energy is lowered. It's the uncatalyzed activation energy minus delta cat. We can go back and take a look at that, and so we can see that the activation energy in the forward direction is the old activation energy up to here minus delta cat. And the same thing will be true for the reverse reaction. It has subtracted from it the same delta cat term. Let's go back and take a look at that. And we can see here that delta cat is subtracted off both the forward E sub AF, and the exact same amount is subtracted off from the reverse activation energy, E sub A reverse. And that's because there's a single transition state in this particular one-step reaction, and it's lowered by the exact same amount, delta sub cat. And so if we just then subtract this equation from the top one, we're left with delta E sub A for the catalyzed reaction, which is simply E sub A forward minus E sub A reverse for the catalyzed reaction, is exactly equal to delta E for the uncatalyzed reaction, because this term, which was the lowering of the activation barrier, is exactly the same for the forward and the reverse, and so it cancels out. And these are equal to each other, and as we set up here, that's also equal to delta H. And so we see that delta H, which is the temperature dependence of the equilibrium constant, is the same whether we have a catalyst present or we don't have a catalyst present. And therefore, K doesn't change with a catalyst. Thanks for listening.